All right, so now you can actually see it. So I'm here to talk to you about passes, something kind of near and dear to my heart. I work a lot on LLVM, and this is kind of at its core. And I feel like we don't often spend enough time kind of going back and reflecting on the core of LLVM. And I've been spending a lot of my time recently trying to work on rejuvenating a core part of LLVM's pass infrastructure. And I was going to give this great talk today, which unfortunately you guys aren't going to get to see, which I do apologize for. I was going to give you this great talk about all the work I've been doing on the new pass manager in LLVM. And I was like, I was looking through the talk, it was going to be great, and I realized that it was going to make absolutely no sense to any of you. Well, to most of you, and that was my fault. I had really structured the talk incorrectly. And I was sitting around with some colleagues and talking to them about it. I would ask them, do you understand this? And they didn't understand what I was actually talking about when I was talking about LLVM passes. And it really sunk in that we haven't really gone back and considered what an LLVM pass is and how all these things work since Chris Slatner was publishing on LLVM. We've kind of just assumed and taken all this stuff for granted, and it's not well understood in the community. And I think that's something we need to fix. We need to do better about that. We need to understand the core internals of LLVM better. And so I was like, this is fine. I'll do a little introduction. So I started writing my introduction, right? And I started writing. I was asking questions of folks who know about LLVM, but they aren't like down in the trenches working on LLVM day in and day out. I was asking them questions about stuff. Oh yeah, you don't know, like that. We need to talk about that too and explain that. Working out this great intro, right? 10 minutes, no problem. I got done and I looked at my notes for the talk and I realized that I had a whole second talk here. And so unfortunately, this is part one. It turns out that there's enough to cover here that really hasn't been gone over in a long time, and there are a lot of intricacies in the kind of core design that we need to discuss and we need to understand in order to even talk about how we might change the implementation of that design. Okay? And so this is going to be a fairly high-level discussion of the design of the passes in LLVM, but it's also going to be fairly detailed, and I'm going to try and take you through all of the gory details of how passes work in LLVM here. Now you may be expecting a few things from a talk that I give. Unfortunately, I've given a few talks which are very funny, very catchy. I've got like cat photos or memes and jokes. You may be a bit disappointed. I hate to break it to you. This is going to be a relatively dry talk in that sense. I don't have memes or dragons. We have a few very confusing moments. Okay, I have one dragon, but it's really just for form's sake. Instead, I'm going to try and answer some motivating questions. I'm going to try and actually help you guys understand how LLVM's passes work. What they are, how they work, how they interact with the rest of the system, and really what makes them tick. So hopefully at the end of this talk, you'll kind of understand the answer to all of these questions. If you don't, I want you to ask questions afterward. I'm going to try and leave some time at the end for questions. I'd like to actually have you guys engaged and ask me for what I didn't explain and make sure that I stick to this and actually give you a good understanding. All right, so let's start with what is a pass in LLVM. We talk about this thing, we use this word pass very loosely in LLVM. What do we mean by it? At its most basic level, it's just an operation on a unit of the intermediate representation in LLVM, right? It's just some totally generic operation. This is a useless definition, right? It could mutate the IR, it could analyze it, it could do anything, it could be a boat, right? This doesn't mean anything, okay? So let's refine it a little bit, okay? The first refinement is, what do we mean by a unit of IR? This is a very fuzzy thing. We can be much more concrete. We have passes over modules in the IR. That's kind of the most basic thing. It is the most fundamental unit of IR because without a module, you don't have IR, right, at a very fundamental level. Okay, that one makes sense. Functions are probably the next really great unit of IR, right? If you don't have a function, we've got nothing to do here. So we've got passes over functions. It's a great unit. What about basic blocks? This is kind of interesting. We actually have passes over basic blocks today, and I think they're a travesty. I'll come back to that. What about instructions? Instructions are actually what people think of as like the most obvious unit of IR, right? Instructions, they are what make up the SSA graph. They're absolutely fundamental to the IR, and they're useless for writing a pass. You have to understand, the unit of IR isn't just the focus of a pass, it's the scope. It's what that pass is actually going to operate on, right? It can't reach outside of this unit. And so an instruction pass, the only thing an instruction pass could do, as a colleague of mine pointed out, is it could strip off flags from instructions. That's literally the only thing we can come up with that it can do. Right? Everything else is going to reach outside of that scope. So it's not a very interesting scope. And it turns out basic blocks work about the same way. The way the SSA graph works, you can't really interestingly modify a basic block while leaving all other basic blocks the same. So I think modules and functions are the best units of the IR that we really have here for passes. We also have some other things. We have three things which I'm going to call a fake, a liar, and a cheat. All right. The SEC pass is a fake. There is no representational model in LVM for the call graph. This confuses almost every compiler person I have seen come in and work on LVM. Just about every single one of them. Why is there not a call graph? Where are the edges? We don't have the edges. And the reason we don't is because we think there's a more efficient representation. We actually deduce the call graph from the call instructions that are already in the IR, right? And we build it up. It's a very ephemeral construct. Well, the unit also is even more of a fake than that. It's not just we don't represent this unit of an SEC. It's worse than that. We also don't actually mean the SEC when we talk about an SEC pass, right? An SEC pass doesn't pertain only to the SEC. It also pertains to every function that that SEC can call, and every function that those functions can call recursively. Right? It also pertains to all the functions which can call a function in this SEC, and all the functions that can call those functions. It's everything above and below a particular SEC. The important distinction is it is not something adjacent to the SEC. That is where you get independence. All right, so that's the fake. The loop pass, though, is a liar. If people want to ask questions, I'm happy for you to ask questions. I saw a hand almost go up. Okay. The loop pass is a liar. Okay, I hate the loop pass. I'm sorry. I really it's not a good pass structure, and I say that despite the fact that it's absolutely important and it's doing really good work. But it's totally broken, right? So the idea of a loop pass makes sense. You want to operate on a particular loop nest within the IR, right? You've got some loop structure. You want to say like that inner loop. I'm gonna run a loop pass over that loop. That works pretty well. Unfortunately, it doesn't actually restrict what it does to that loop. It modifies the containing loop all the time. It essentially has to, because everything that loop passes do is to simplify or to move instructions out of the loop. That's kind of what you want to do, right? And so it's got to modify the containing loop. And worse than that, even the outermost loop pass is still a lie, because it has to modify the containing function. And worse than the SEC graph, as you modify these containing structures, you're actually impacting adjacent loop structures all the time. It will routinely just go and simplify a bunch of instructions further downstream, because, it can now, right? But that means it's a lie. It's actually a function pass. Like, all the loop passes really should be function passes. It's very, very confusing. It's one of the most confusing parts of our pass structure, but it still serves a purpose. We're actually going to talk more about the purpose of the loop passes later. The immutable pass is a cheat. So the immutable pass exists only because of problems people ran into with the existing pass infrastructure, right? And they didn't have a good solution to those problems because the existing pass infrastructure is very complex and it's very hard to change. So they took a cheat. They said, like, well, what we'll do is we'll define this pass outside of the existing pass structure by saying that there is no unit of IR which it pertains to. None at all. It simply exists in the ether, beautifully or something. You can see the old data layout pass as an example of this, or alias analysis is another good example of this. But these are cheating, right? They're just cheating around the limitations of the infrastructure. What they want to say is that the results of this pass are immutable, that they can't be invalidated, that they persist forever. They don't actually want to be something that doesn't pertain to IR. In fact, most of them pertain to the module. And even if they don't pertain to the module, they pertain to something inside the module. But we can't represent this today, and so we cheat. It's not unreasonable, but it's really frustrating. And I do want to emphasize, I've kind of critiqued three things here. The fakes, the liars, and the cheats are all really important. They're solving very real problems in LVM. We do need them, right? They weren't added frivolously, right? They were added to solve a problem. So don't get too hasty. All right. So Let's break down these passes along a different dimension. So we've looked at how the units of IR break down in a pass. But the other way to kind of think more concretely about passes is to think about the actual nature of the pass itself. It's not just a generic operation on a unit of IR. There are more specific operations that dominate. In fact, there are two. The first one are analysis passes. Now these are kind of interesting beasts. They're very theoretically refined. They don't mutate the IR in any way, right? They compute some higher order information about the IR, right? They tell you something that's hard to figure out in a nice interface, right? Dominator tree is my favorite example of this, right? We have a dominator tree pass, right? It produces a dominator tree for a particular function. It doesn't mutate the function, it doesn't change anything, but it exposes a good interface to very important high-level information. Okay. One analysis pass can actually use other analysis passes. This gets to their real power, right? When you have an analysis pass, you don't just have to rely on the IR, right? You can actually take the IR and you can take other analysis passes and you can combine them. You can build more interesting analyses on the IR, right? And this is how every single analysis in LLVM works. If you look at the loop information analysis, which tells you about the loops, it's asking the dominator tree analysis about the dominant structure of the code, and it's going to ask scalar evolutions about things. You're going to have this building up of different layers of analyses, and this forms a really nice thing, all right? Because these passes are immutable, right? And as long as you don't have cycles in their dependencies, we can always arrange to run all the passes we need to compute all of these high-level pieces of information, right? Cycles are bad. We can detect those. As long as you don't have cycles, you don't mutate the IR, right? Nothing changes. You're just building up layer and layer of more abstract information. It's really, really nice. The other nice thing about analysis passes is that we can cache them, and we can cache them very aggressively. Until some part of the IR that they're analyzing mutates out from underneath them, their results remain valid. And that means that even relatively expensive analyses can be run in LLVM's passes, right, without undue cost. And that's very, very important. We actually try to factor a bunch of the most expensive things we do in LLVM into an analysis so that we get caching effects. The other kind of core type of pass is the transformation pass. Okay, these passes are the ones that actually mutate the IR in place. They're going to, look at the IR. They may actually consult analysis passes to find out higher level information about the IR, perform some optimization, some transformation that's going to, shift the IR to a different but still valid form. Now, I want to reiterate, it's a different but still valid form. Okay, it's really, really important when you have a transformation pass. It's always transforming valid IR into valid IR. This is one of the oldest principles of LLVM, goes all the way back to when Chris first talked about LLVM. It's absolutely critical because this is what allows you to just arbitrarily recombine the passes of LLVM in new and interesting ways and figure out more interesting ways to optimize your code. All right. One wrinkle. So transformation passes, pretty clearly in my mind, should not be able to depend on other transformation passes. I actually say they cannot effectively do this because you get into these weird contradictions, right? You have one transformation pass which wants another transformation pass to be run, and that one wants some other one to be run. But the first one wants the first one to be run. You can get cycles. Can't break the cycle, okay? You can also get problems where you have one transformation pass, it wants two different other transformation passes to run first, but which one, you have to pick a serialization here, right? You've got the IR, we're mutating it in place. We can't do two different transformations, separately. We have to pick some order. There's always going to be an order that's wrong, right? Worse, you may have an order that flat out invalidates it, and you've gotten a cycle that you didn't even see when you were writing your code. It's very, very problematic, all right? So I don't think this is a workable model, unfortunately. LLVM actually does this today, and it does it does it in several very hard to change places. So this is kind of a problem we have with our model so far, at least today. Okay, we talked about what passes are. A few questions about what passes are. We kind of shift focus a little bit to how we actually combine these passes into more and more interesting, ways to optimize code. Okay. No questions. Silence, okay. So passes aren't functional. So we can't use functional composition with passes, right? They mutate in place. So we have to kind of have some scheduling idea. We have to actually like iterate through passes on the same set of IR. There are kind of two dimensions to this that are really interesting. The first dimension is running multiple passes over a single unit of IR, right? The classic example here is like your function pass manager, right? You have a function pass, right? It is a function pass. It operates on a function of IR, right? But you would like it to actually run a bunch of other function passes for you, and it gives you a nice kind of compositing effect. Pretty straightforward. And then there's a little bit trickier dimension to this. There's the idea that you might have a pass which is actually going to take a module, and it's going to run some function pass over each function in that module, right? And that's kind of decomposing one unit of IR into finer grained units of IR. And these two forms are how we kind of build up a set of passes into a really rich pipeline that can handle all the different aspects of the IR we see. Now, in the current implementation, it's actually really hard to see this design distinction between these two pieces because they're totally conflated. All right? The function pass manager does both halves of this job, and it makes it very hard to express things in a composable way. Something I think we very much need to fix. Come on. There we go. Now, once you have these aggregation systems, right? Once you can aggregate across multiple passes, all of which iterating pertaining to a single piece of IR, and once you can take a single pass which operates on a single unit of IR, right, but decomposes it into smaller units and runs some other pass on each one, you can build up interesting pass pipelines. And LLVM kind of cans up a bunch of this functionality in its pass manager builder. If you've ever hacked really heavily on LLVM, I hope you've run across the pass manager builder. It's a little bit shaky, but it's really useful. What it's doing is it's kind of pulling together common use cases, common patterns of lining up a sequence of passes, right? And it's making them easy to use, easy to plug into, easy to parameterize in known ways that are going to work together very effectively. This is used by Klang's, O3 flags. It's used in opt. It's used all over the place. Make sense? So let's talk a little bit about what these pipelines of passes are, because as interesting to me as the actual passes are, the combination of passes gets very complex. So there are three phases of IR optimization. I'm going to assert this. This is somewhat disputed in the community, but I think this is pretty close to accurate reflection of our current state. We have the first phase, which is essentially doing cleanup and canonicalization of the IR. Second one is going to do simplification and further canonicalization. And finally, we do very target-specific optimization and lowering. So first off, you'll note that I mentioned canonicalization. I hate to do this, but we need to take a little brief digression about canonicalization. You've probably seen canonicalization bandied about on the mailing lists a few times, maybe once or twice. There's a lot of questions about why we care so much about canonicalization. Why is LLVM even thinking about canonicalization? It comes down to a very, very simple thing. There's more than one way to do it in LLVM's IR, right? You can write the same expression hundreds of different ways in LLVM's IR. They're all equivalent. We have no real way of telling them apart, okay? When you start combining multiple operations together, right, you get a combinatorial explosion in how many different ways you can write a particular piece of code. We don't have any good way of actually handling this combinatorial explosion. If we actually see this combinatorial explosion, the optimizer shuts down and goes home, right? There's nothing you can do about it. The only way we have to handle this is actually just to pick, for every single operation, a single particular representation that we're going to use. And we're going to force it into that representation every time we find something equivalent. And then you can actually combine those together to get combinatorial effects of canonicalization, right? And that's actually what allows LLVM to scale its analysis reasonably, right? You've got this kind of combinatorial micro-canonicalization, which then leads to macro-canonicalization, right? Combining the effects in a very reasonable scale. And once you know that the IR is canonical, you have one pattern to look for, not n patterns to look for. And this is really, really, really important. So that said, a lot of people will talk about LLVM as a canonicalizer. This just bugs me, okay? I understand where they're coming from, right? It's important that you get people to realize that the primary goal of LLVM's first two phases of optimization has very little to do with traditional optimization, like what executes fast on a machine. That doesn't even come up during the first two phases. It's just not relevant, right? And it's important to get people to realize that. But canonicalization is a part of optimization, right? It is actually making the code simpler in almost every case. More importantly, LLVM at every stage is not just canonicalizing. That's a really terrible misunderstanding, right? It's also simplifying. It wants to find a simpler form, and it uses the canonicalizations to recognize them efficiently, right? That's the key piece. Okay, sorry for the brief digression. Back to the pass manager, or the pass pipeline. Okay, so I mentioned there were 3 different phases of the pass pipeline, right? The first one is cleanup. The point of having a cleanup phase in the pass pipeline is to make writing front ends simpler. Writing front ends can be really, really complex if you don't have a strong cleanup phase in your optimizer. It forms SSA, right? It cleans up all of the kind of crufty alakas you've got. It gets all of your variables from loads and stores into like nice SSA registers, right? It's going to lower front end specific things that only exist to make writing a front end easier. One of the best examples of this is the LLVM expect intrinsic, right? Which is totally redundant with the profile metadata, except that profile metadata is actually very hard for front ends to emit, and the expect intrinsic is easy. We actually move it into the metadata inside of the optimizer where we have much more information about the control flow structure, and we can map from this intrinsic the front end understood across to the control flow that you want metadata attached to. It also does some initial canonicalization. The reason it has to do some initial canonicalization is that if you don't do an initial round of canonicalization, then nothing else works. Right? We have to get everything into canonical form so that we can recognize the canonical form in every later stage of the optimizer. And so the cleanup involves some of the more heavyweight canonicalization efforts just to kind of bootstrap us into a good state. Okay. The cleanup, though, is pretty small, relatively speaking. There's not a lot of complexity in the cleanup phases. There's more complexity in the simplification phase, all right? The simplification phase starts off at the outermost layer doing interprocedural optimization, okay? And the framework for the interprocedural optimization is this SCC passes, right? These SCC passes that don't actually operate on SCCs because it's fake, sorry. Okay, the interesting thing is that this outer framework actually contains the per function optimization and all of the finer grained optimizations, right? We nest them inside of it. And so this is where you start. You start interprocedurally, and I think that's very important to getting strong interprocedural results out of an optimizer. So once you have simplification, right, how does this interprocedural optimization work with a call graph and SCC-based optimization? And this is kind of where it gets tricky. The core idea here is to use pairwise interprocedural optimization, just looking at a caller and a callee pair across one call edge, right? That call edge is something we can actually reason about fairly well. It scales well, right? It's linear in the number of edges, even though it's not linear in the number of functions. And so it still scales well, but it allows us to do a lot of really great interprocedural optimization. And in order to make this work well, we have to realize something, right? The functions that you're looking at during this interprocedural optimization, they need to have been canonicalized and simplified for you to analyze them. If your call E is raw right out of the front end, right? If it hasn't had its loops deleted, its dead code eliminated, and all of the other brokenness in it fixed, you can't analyze it. You don't know if it's a good thing to inline. You don't know what properties hold for the function arguments. All of these interprocedural optimizations don't work. And so this SCC optimization process has to work from the bottom up. It starts at leaf functions, which don't call anything, and it just runs these nested optimizations on them to clean them up. And then it works up the graph so that at every point you have maximum context for doing your interprocedural optimization, right? At every point you can look at the edge in the call graph, you can look at the callee, and you understand exactly the nature of that callee, what it's doing, and how it works. And that's really the core idea behind this call graph SCC-based optimization. Strongly connected components. Sorry. Thank you for the questions, though. I'm happy to clarify any terminology. Everyone familiar with strongly connected components? Okay, just checking. Thought I would check. All right. So there are a bunch of optimizations that happen in LLVM inside of this phase. I'm just going to mention them here because I'm trying to give you guys some context about if you wanted to know where this type of optimization happened in LLVM, this is where you should go look, right? Argument promotion, maybe even, we could do argument deletion in this context. Currently we can't, but it might fit, right? Call and argument attribute synthesis. So if you have a call, right, and you can prove that the function you're calling doesn't mutate memory, we can synthesize function attributes for that. More interestingly, if we can just prove that for this particular call site, there is some special property, we can synthesize an attribute just on that call site, on the edge itself, right? And that's very, very powerful. This is where we do inlining, right? This is hopefully where in the future we'll do outlining, we'll do interprocedural constant propagation. We can do lots of things in this context. But the other thing we do in this context is all of the per function things. So let's talk a little bit about those.
Sorry, Chandler.
Yes?
Cloning happens here too?
If we did cloning, if we did partial specialization or specialization, yes, it would happen here. I mentioned outlining. I should have put specialization and cloning. All of those things would absolutely happen here. All right. So per function optimization. These are primarily run within the SEC over each function, right? The SEC pass is going to first try and do the interprocedural things, and it's going to run all of the function passes over each function at SEC. Now, interestingly, this process is iterative in LLVM. It's then going to go back and try the interprocedural optimizations again in case it needed both sides of that call edge to actually be optimized to understand a particular transformation. And so it's going to be very iterative in this process. But within the actual function optimization, it's actually pretty standard. This is where things get a little bit more normal, right? We have the decomposition of aggregates. We do reassociation. We do propagation of values through memory, right? All the kind of standard things. We also do our loop optimization. The loop optimization is where things start to break back outside of common and expected optimization passes. But generally speaking, about 80 to 90% of the optimization passes people tend to look for, want to write, or anything else, they fit here. They walk over a function, they do some transformation on that function. All right, so let's look at the loop optimization passes, because in LLVM, the loop passes are kind of weird. I already gave you some indications of this, right? There are lies, there are all kinds of problems with the design here, but they're interesting problems, and they're there for a reason. So the loop passes actually walk over a particular loop nest from the inside out, which is a little bit strange, right? They start on the innermost loop, then they go to its containing loop, then they go to its containing loop, all the way until they hit the bottom. And they do this for a particular reason. We want to run all of the loop optimization passes on the innermost loop before we even look at the containing loop. Because if we don't do that, when we look at the containing loop, we're not going to have any idea what's going on. Right? I gave a simple example here, right? You rearrange the structure of the loop, suddenly the result's computable, right? Great, we compute the result, the loop's now dead. We delete the loop. Fantastic. Now, the outer loop, the result of the outer loop is now computable because there's no longer a nested loop, right? It's just an induction variable. It's fine. It's very straightforward to compute. But if we have a standard optimization phasing here, right? We've already done the figure out the result of the loop computation phase. How do we come back to it? The way that LLVM does this is by walking from the inside out across the loop bodies. Make some sense? Excuse me. All right, so we have some loop optimizations. I actually think this is one of the big weak points in LLVM. I think we don't have as many of the advanced loop optimizations as we really should. We have rotation, hoisting of invariant code. We unswitch loops. We do the induction variable simplification that are needed, right? But the thing we really don't do is we don't do interesting and aggressive transformations of the fundamental loop structure, right? You can see some work to try and address this in Poly, right? You can see people talking about doing this even outside of Poly. I think this is actually a big open area for LLVM. And a lot of people are surprised when I say that. I want to just add a brief anecdote here, right? So understand, I don't actually have any loops that matter in terms of performance, like really matter, that I care about. It rarely happens, right? There are a few of them, but by the time they matter that much, the developers working on the code, they've gone in and they've hand-tuned that loop until it's perfect. This doesn't actually happen very often. What I really dislike is that I actually find developers routinely spending tons of their time hand-tuning these loops that they think might matter. I mean, I can tell them that their loops don't matter, but maybe they've got one edge case where it matters, and they spend, I don't know how many days, weeks, and months tuning the layout of this loop, manually fusing loops together, all of this just to get their loop to improve like 20% runtime for one use case. Maybe it matters, maybe it doesn't, but they do it anyways. We should do better here. We shouldn't make the developer do that. This is what optimizers are good at, right? And so I really do wish we'd kind of push this forward some. All right, I'll get off my soapbox there. All right, so the last phase of optimization is lowering. And this is where everything gets a little bit sticky, because at this point, we can no longer hold to that canonicalization principle. All right, this is about producing target-optimized IR. Now, a lot of people get confused here, and they think that we're going to lower to some different representational structure. Like we're going to have IR and then lower IR, which is different and has different instructions or intrinsics or all kinds of other crazy stuff. That doesn't happen at LVM, and there are a lot of reasons why, right? Instead, lowering an LVM is much more about forming patterns, right? We're still using the same representational model. It's still valid IR, right? We can still do everything we expect to do with IR in this phase. But we're forming patterns that are very, very useful to the rest of the optimizer. Either they're useful for executing fast on particular hardware, in the case of a vectorizer, right? Or they're useful for kind of recognizing common patterns, idioms, if you will, when you're actually going from IR into the actual code generator itself. So the primary thing here, as I mentioned, is loop tuning, right? And this is kind of your standard loop tuning passes, vectorization, interleaving, unrolling, all of the things that you want to do, strength reduction, all the things you really want to do to make sure that your loop is going to execute very fast on a particular piece of hardware. The way I like to think about this is about lighting up more of your silicon, right? Your chip has a lot of silicon on it. Most code doesn't use it. This is about making most code actually use the silicon on your chip. Then we have kind of target preparation, right? Things that are trying to prepare, okay, you've got some IR, we know what it looks like, but it's very hard for us to actually code generate that IR. We're going to put it into this kind of brief, stubbed out form that's going to be a lot easier for us to generate code for. You can see this in CodeGen prep. People have historically kind of pushed back against this, and recently there's been a lot more interest in actually just leveraging this to do more intelligent code generation from complex IR structures. So I think that's probably a healthy move. All right, we're done. I blazed through that. There have to be some questions. It's been just dead silent here. So, what do people want to know? I can go back over things, but I feel like I've just blazed through it too fast. So, in summary, right, we have these passes, right? They operate over IR. Analysis passes are doing this like pure analysis, computer result for a particular piece of IR, right? Transformation passes, they're actually like going, looking at the IR, figuring out a better way to do it, rewriting the IR. The pass manager builder, right? We have all the pass pipeline details. Okay, some questions at least. Thank you. Okay.
Yeah, one question is that, in general, how much...
Hold on, I think we want to get a microphone for you. Blaze through that.
Yeah, we're recording this, so where was the question? Thanks. Yeah, so I'm wondering, how much target-specific knowledge is available at that level when doing things like loop analysis? And in future, are we going to have more or less of that available?
That's a great question. So right now we have this somewhat suspicious interface that I may have contributed to, which is this target transformation info analysis, which is not an analysis at all. It's just this like wedge between the target and these loop passes. And if you look at its interface, right, you can see all of the information that a front-end loop pass or some other pass has about the target. And it's not really complete yet, so if I go back, the target preparation phase, right? This phase is still actually directly querying the target, and we haven't moved all of the information it needs into this interface. But most of these passes are actually already using that. So our vectorizer has a pretty good idea of the cost of forming particular vector operations, particular vector data structures, the width of the vector unit. We understand those costs and trade-offs pretty well. I think the biggest thing that's missing is understanding more about addressing modes and kind of the particular idioms that we need inside of the IR in order to lower effectively. And there's some work going on to try and push more in that direction, but I'm really hesitant to predict how much more we're going to get. As far as I can tell, right now we have a good amount of information about kind of the execution domain, which allows us to make good decisions about how loops should be structured, but we have relatively poor information about the particular instruction selection process that's going to take place. And that means that we have a hard time doing the last kind of phase of target preparation. Does that answer your question?
Yeah, thanks.
Other questions? Yes. I'm worried about you.
So cogen, like once you get cogen, is that part 2 of the talk, or?
So part 2 of the talk is not about cogen. Part 2 of the talk is about how I'm hoping we can transition our current pass infrastructure to actually cleanly model this design and not have all of these pledges. And the somewhat surprising challenges that come up in actually building that. Because it turns out that this design is kind of how we think about passes, and this is not what the current implementation does in all cases. And there are a bunch of problems that I kind of touched on. And I think that we can solve those with a better set of infrastructure around passes.
So the question really is like, what's currently in cogen passes, and what do you think should move more for cogen preparation or to the same structure?
So the question is, what should we do once things hit code generator? I don't have the faintest idea. I think you should ask, a bunch of the other people that work on the code generator, because I try and stay far away from that part of the compiler. I don't always succeed, but I try and stay far away. I genuinely don't know. I think there are a bunch of possible designs in the code generator that could work. I don't think we have anything, we don't even have a design for the code generator passes, right? So I couldn't give this talk about the code generator because code generator does not have a good definition of passes at all. I don't know how to give that talk yet, and I think you need the code generator people to get up here to even explain what the current design is.
We haven't started a new design with some of Tim's atomic lowering stuff.
And it's the third attempted new design.
In the last 12 months?
In the last 12 months. So I think that's an important question. I don't know if anyone does have an answer. It's certainly not me though.
So I think one common pattern, like I hear people are often asking questions, a pattern I don't understand myself is basically I have like some module pass which actually needs some information, maybe some information about the loops in a function.
Yes.
And I haven't seen you talking about that pattern, and it comes up to me very often. Is there something to say about it?
Yeah, I should have spent more time talking about that. That's hard. So I hinted that the more interesting part of this is this piece, right? And that actually gets to your point. So there's one aspect of decomposing a unit of IR into smaller units, right? And running kind of the transformation passes over those smaller units. But what you're asking is, how do you actually decompose the analysis passes? And how do you actually map those back and forth? I think the essence of the answer is, well, in the obvious way, right? If you're a module pass, you should be able to query for a function analysis pass, and it should go run and compute that function analysis for you. And today that actually works, but it works because of a bunch of terrible kludges inside of the pass manager. And if you're not a module pass, if you're an SEC pass, it stops working magically, which is the problem with SEC passes today, right? It's actually the problem with LVM's optimizer today. But the solution to that's not interesting from a design perspective, right? The answer is clearly you should be able to do the query, you should get a result back. The hard part is actually how do you implement that query? And that gets into the whole second part, which is like, well, it turns out implementing that's hard. It involves caching, and it makes the cache invalidation problem much harder. Because how do you, like, which analyses do you invalidate when you change a function? Right? You invalidate the analysis passes over that function, certainly. But do you invalidate the analysis passes over the SEC containing that function? The module containing that SEC? Clearly, you have to. If you're doing that invalidation, how do you actually preserve analyses long enough to actually be able to query them across these units of IR boundaries? And I think this is essentially the interesting part of, or at least one of the most interesting parts of how you implement this. But I hope that it doesn't impact the design. The design should be just kind of obvious. It's like, well, you can query it, and you get the answer.
Okay, I see that. So do you, like, one kind of like one follow-up question, I'm like looking forward to being able to do so in all cases. How much interaction from the programmer do you expect? Could I just query an analysis and it will always work, or do I actually need to think myself about like making the caching, like do I contribute to making the caching efficient? Do I need to contribute there?
I don't have a principled answer to that. I don't know if there's a right way to do it or the wrong way to do it. I can spill the beans and say what happens to work with the design I'm hoping to use. What happens to work is that if you are in a kind of lower level unit of IR and you query a larger unit of IR, either that larger unit of IR's analysis pass is cached or you can't make the query at all. And you don't have to think about this because you get a compile time error if you try to do it, right? The only interface you have available is a cached interface. You can't run the analysis on the higher level of IR. And the reason is pretty simple, right? You're inside this narrow scope. You can't pop out of your scope and analyze the entire module, or you've lost the kind of separation of concerns there. So on the flip side, if you're in a module pass, there's nothing you can't do, right? Because you have the whole module, you can do anything, right? The hard part, if you're a module pass, is if you change a function in some way, right? You actually have to update the analyses, right? You have to invalidate the analyses yourselves because you can't rely on the passes invalidating them for you. But it's no burden on the programmer because it's kind of like, it's there in the API. You'll see it. Other questions? I saw a question up there. But hold on, you need the microphone.
Thanks. You mentioned ILP. What does that stand for and what is it?
ILP. So that stands for instruction level parallelism. And if you want to understand it, I would direct you at Jacob's excellent talk a year ago here. Well, Paris, but.
Right, thanks.
Other questions? We need like 2 microphones. We could parallelize this.
For normal complication process, so how do you expect the compile time change if you apply those path management improval?
I don't expect the path management improvements to have a very significant impact on compile time. I would like to think that it will get better because we will cache analyses more effectively. Right now the caching, right? I mentioned that you can cache analyses. We don't do a good job of it, but not for any good reason. If we do a better job of it, we'll run fewer analyses. Maybe that will improve compile time. I wouldn't hope for much there. What I really hope is that we'll be able to do more in approximately the same compile time.
Okay, thank you.
Other questions? Still got plenty of time. Aha, Kostya.
What about parallel execution of the passes?
Well, should never have given you a mic. So, I would like that. I think everyone would. I think it's hard. I think that it very fundamentally comes down to this idea that we actually have these units of IR, and they expose opportunities for parallelism between passes over independent parts of the IR. But in order to do that, this fake liar and cheat, they're going to have to clean up their act. And so that's the thing. I think it's too early to really go too deep into the parallelism. I'm very hopeful, right? I'm very hopeful that we're going to have the ability to aggressively parallelize the pass manager once we kind of clean up our act and we get very serious about, when we write a function pass, we mutate that function and not the module and not other functions, and we don't disrupt things. But right now, there's very little enforcement of this design principle. It's a principle, right? We try to adhere to it. We have code reviews that catch things, but nothing checks. To parallelize, we're going to have to check. And when we do, I know that we're going to find problems. I can rattle off a list of passes that violate this. That said, I think I'm optimistic, but I don't want to promise a lot. How much more information do you want?
I want it to be done.
Well, I do too. I think it's a lot of work. I think very fundamentally, until we have a strong implementation of these principles and the ability to check them, it's hopeless, right? Trying to do it is just a waste of people's time because you'll just spend all of your time debugging things the hard way rather than the easy way. I think once we have that in place, the debugging will be easy enough that we can actually make it happen. And I think that Michael may be about to disagree with me, but no, okay.
So what about, we have this come up every once in a while, running different passes on different parts of a module. You want to optimize different functions differently.
Don't we have function attributes for that?
So as Eric says,
Yeah, so we have a way to represent that, but do we actually have a way to implement this? Well, I know we don't now, but...
So I like the design of passes and the aggregation of passes that don't deal with that because it's simpler, right? It's much simpler. I also think that I think that that's a somewhat suspect desire. Personally, I think that when you're asking for that, what you're actually saying is, well, I have a temporary problem. Right? I've got this short-term problem where this one pass does this one bad thing or doesn't do this one good thing, and so I can't use it everywhere or I can't use it on this function, right? And you're trying to solve it. I don't like designing things around that. I think that it would be better if you didn't have that property in your passes, if passes were able to detect when they were useful for a function. You can run them everywhere. They run. It's a simpler model to debug, to understand, to work with, so on and so on and so on. That's my opinion. I don't know that will carry the day, but that's certainly the direction I'm pushing it. Other questions?
Hi. Staying on this slide here, you say that there's not really any interesting passes you can do on basic blocks or instructions.
Yes.
Doesn't that mean that's because of bad design? Shouldn't that be possible and neat? For example, constant folding on an instruction, shouldn't that be possible?
Why would you want an instruction pass for that rather than a function pass to fold all constants?
So
But you want the effect to be local, right? So you could recurse in and say, run it on every instruction.
But you want to start up the pass machinery for your pass to run it on one instruction, have it stop?
No, you run it on all of them.
So you run it
Sequentially.
across basic law?
Right, but this is just composition, isn't it? What was on the next slide? Was it the next slide?
There's a non-zero overhead to running a pass though, right?
well, no. So I think the question is valid. So the question is, as a convenience, why couldn't we have passes which were inherently structured as instruction passes or inherently structured as basic block passes? And I think that the answer is the structure you're looking for makes perfect sense. I just don't think it's part of the pass. Okay? And I'll explain what I mean by that. The pass, the IR unit that the pass pertains to is really about scoping. It's not about convenience or even what you're going to transform. It's about the scope you're allowed to reach across. And it's very hard to transform an instruction and not touch any other instructions in the IR, right? That's quite challenging in most cases. You're at least going to usually change the uStef graph. So as a consequence, I don't think that the scope of instruction is useful. And while it is possible to change basic blocks without mutating other basic blocks, that's actually also reasonably hard, it's fragile, and it doesn't seem like a compelling motivation. So as a scope, I think function is the more appropriate scope because of how LLVM does SSA structure. That's what it comes down to. Now, that doesn't mean that it's not useful to have a really convenient way to write an instruction-based transformation. We actually have one of those. It's called inst-combine, right? Inst-combine is like this huge pass to eat all other passes. It's actually about, several hundred other passes all rolled up into one. If there were an instruction pass, it would be inst-combine. And the way inst-combine works is that it actually has a bunch of infrastructure to just visit every single instruction in the function and to dispatch across a very wide range of functionality. We could formalize that infrastructure into something else that was reusable for inst-combine for some other instruction level optimization, right? And in fact, parts of it already have been. There's an instruction visitor and an instruction iterator utility in LLVM that try to make this exceptionally easy to implement. Right? And we could do more to kind of layer more infrastructure on top of that, but I don't think that's part of the pass. That's part of the utilities that make it easy to write a pass. And the reason is that I want the unit of IR to remain a scoping unit of IR, because I would like to get to what Kosh asked about, which is parallelism.
Okay, thanks.
More questions? All right, Raphael. Round two. Oh.
You've learned.
So for the parallel case, you said, for example, a function can query information about a module as long as it's only a cached information. So for example, it could query like how many colors do I have?
That makes sense to me.
So in a parallel case, what's the idea is you always get like a conservative view because other function might be being optimized at this very moment and remove the last call to this function you are currently optimizing. You'd ask how many colors do I have? It gets 1, they're guaranteed to get 0 or what?
Cache validation is hard. Yeah, I mean, fundamentally, yes, this is a problem, right? I think that it's going to be very hard to cache module level analyses like who's calling who across transformations which mutate the IR in any way, shape, or form, right? And so essentially, the way I like to think about it is unless there's some reason why my pass knows that in querying this cached pass, neither my pass nor any other parallel pass could have invalidated it yet, right? Before finishing running, I don't get to use it, right? And there's various things we can do to kind of make this easy, right? We can make the thing which drives the parallelism eagerly invalidate things which are going to become invalid in a non-deterministic point in time. And I think that's actually tractable to do. That may be too aggressive, right? That may invalidate too much. We could take more fine-grained approaches, but I think there are a lot of interesting ways to do that. And again, this is why I don't want to promise too much with parallelism. There are going to be hard problems that we solve here. There's going to be this problem. There are going to be other problems. I mean, like if you guys want to think about what's really hard with parallelizing, how do you make updating the uStef chains of globals and constants not a point of serial, like a point of contention? That's one of the really hard ones. You have to be able to add another use to the constant 0. Other questions? Did I answer your question, Raphael?
Yep.
Okay. Other questions? We still have like 6 more minutes. You've got time.
Could you say that again? What would be the really hard one?
One of the really hard ones, not the really hard one. One of the really hard ones is, so how do you make the update of the uStef chain of global values, such as constants, not a point of contention if you're running passes in parallel? We don't have answers for a lot of these questions yet.
And what's the really hard one?
If you think that's easy, I mean. By all means.
You said it wasn't the really hard one.
No, I said it's one of.
Oh, one.
One of the really hard ones. Other questions? Going once. Going twice. All right. Thank you very much.